Hi there, it's great to see you. I'm LALS, the Anthropologist, and welcome to my channel, Human Evidently. On this channel, I post a weekly lecture on topics related to my studies in anthropology, especially those relating to mid to late Pleistocene hominins. Today, we're talking about a topic that is a mixture of my two areas of study. I have a bachelor's degree in geospatial intelligence from American Public University, and am almost complete with a bachelor's of science in anthropology. This is a lecture I developed on modalities of digital archaeology, based on my learning at a field school this past summer. So the premise for this presentation is that I would present it at a conference for people who are unfamiliar with GIS and remote sensing, but want to understand its uses for anthropology, archaeology, and CRM. First question, can a layman use orthophotos, surface modeling, and 3D models to document sites and artifacts? The answer is technically yes. This is something you can start doing from home without access to a remote sensor or a UAV. Organizations like OpenAerialMap.org make high-quality UAV data available to the general public for processing. Second question, has remote sensing supported mid to late Pleistocene site detection and documentation already? Yes, but not enough. Today's presentation primarily focuses on use cases I have personally worked on in the American Southwest, but at the end I will briefly touch on recent research that has been conducted utilizing similar tools for much older sites. Third question, are these tools accessible to those with minimal funding? Yes. The tools I used for this project, aside from the actual drone, camera, and computers, are all open source and available to the public, free of charge. The basic steps for utilizing open source tools to process your data are, after capturing over 35 images with 60 to 80% overlap, you can use QField to provide accompanying georeferenced point and polygon mapping, use WebODM or Meshlab to automatically stitch the UAV data together into an orthophoto, surface model, 3D model, or GeoTIF file. Use QGIS to integrate those above components into raster and vector features, eventually developing a useful layout output for a report or simply a working map stored on the GIS interface. When it comes to sensor data, you can use open source imagery, but if you're wanting to look at a specific site or feature in high definition, you may want to acquire and use your own drone. You can hire an expert, but for some, it's worth it to become their own expert. You'll need a Schedule 107 to fly a commercial drone in the United States. This is a test you pay to take, but it's free to recertify yourself every 2 years. Every project will be different, but in general, here's what you'll need before you fly. 1. Your Schedule 107 and the knowledge that comes with that. What airspace are you in? Do you need to be in contact with air traffic control? Are you familiar with aeronautical decision-making? 2. Permission. What are the site access requirements? 3. This one goes along with getting permission. Are you complying with the laws for the region? Some locations will require certain specifications for your drone and its components. 4. Communication. With any necessary government agencies, tribal historic preservation officers, landowners, stakeholders, or community representatives. What do you need to do if you find a culturally significant artifact? What about if you find human remains? 5. A team. Your team should be aware of their roles and responsibilities. If you are the remote pilot in command, you are in charge of all things surrounding the time you're in the air. 6. The weather. Check it in advance, but check it the day of too. It can change, and it does impact your ability to collect good data. 7. Your aircraft. Is it ready to fly? Is it operational? What about the tools and components associated with it? Now that we got the basics out of the way, let's talk about the realities and capabilities of this technology. This is Site 1. What you see here is an RGB orthophoto generated from around 300 photos collected with a DJI Mini 3. RGB means the image has 3 bands of light, red, green, and blue. For this project, my VO, visual observer, and I did a walking survey of the area, and planned out a path to manually fly our drone over this field in the hopes of getting a clearer map of what we suspected was an anthropogenic feature in the landscape. That day, there were very gusty winds, so we made the choice to fly lower to the ground to conserve battery and keep the drone safe. As a result of our low flight altitude, this orthophoto, when processed with WebODM, omitted the trees on the site. Additionally, the wind blew clouds across the field at a fast pace, impacting overall image quality due to irregular lighting. Stuff like this happens even when you plan things out. The weather is never precise, and it can turn on a dime. To compensate for the quality of the data we collected, I used the overlay feature in QGIS to allow the trees from the base map layer to come through to the top and dilute the irregular shading from the migrating cloud cover. This goes to show you that even if you think your data is a total bust, it is often still worth trying to process it anyway. Thermal cameras detect temperature differences between materials, especially useful for historic sites where you may find walls, irrigation, or other structures. It is, however, very dependent on time of day, ambient temperature, and seasonal conditions. I did not have time to complete a thermal imaging project during the workshop I attended, so instead I will put resources for that kind of work in the description below. This multispectral imagery is from Site 3, which is a very large site appearing to contain circular platforms, multi-room dwellings, extensive lithic scatters, and redware pottery sherds. The planned transect paths I chose cross between two man-made tanks, over a dry stream bed and a Forest Service road, and across an elevation change along a steep hill. The pre-planned flight path used GPS tools to keep the drone at 86 meters above ground level. Multispectral image data allows you to play around with the mathematical representation of the pixels shown from the different spectral bands. If you recall, the RGB image toward the beginning of this presentation had 3 bands: red, green, and blue. These are all within the section of the light spectrum that's visible to humans. The multispectral sensor on the DJI Mavic we used for this image collects 5 bands, including green, red edge, and near infrared. Most sensors that collect more than 5 bands are satellites in low Earth orbit. Multispectral imagery allows us to create a visual representation of the vegetation and soil health called a vegetation index. In addition to highlighting ecological risk factors like dry or sick trees, a vegetation index can also make anthropogenic features more apparent due to the way non-vegetative materials reflect certain light bands. When not generating a general vegetation index, deciding what false visualization method to use is often a result of trial and error. The false color representation I chose for this project is an inverted magma gradient of the color band 2, green, separated by quantile into 52 colors. This allowed me to bring the features of interest, in this case rock piles from pre-contact structures, into clear view despite suboptimal lighting conditions and moderate to dense forest cover. In the layout, you can see a section I chose to magnify, which gives you a closer view of the rock piles of interest. You'll notice that the multispectral imagery is very high quality, and the resolution is very crisp. Depicted here is a line of best fit drawn by me to show the rows of structure ruins that lead up the side of this hill. Between the 2 middle rows is what appears to be a dry stream bed. Using RGB imagery alone would have yielded results that were much more difficult to interpret. I suspect this will be a site of interest going forward and hope there will be efforts to catalog and date this space, which seems to have held a large population of people pre-contact. Now we're back at Site 1, using the same photo imagery that was used to construct the RGB Orthophoto a few slides back. I chose to add this slide because some people may not have access to multispectral or thermal imaging, but that doesn't mean you can't adjust the aspects of your RGB orthophoto to bring out certain features of interest. It can take time and energy to figure out what works best. In this case, I played with the blending mode, here it's set on lighten, and grayscale by luminosity to bring out the rock piles. To further clarify the image, I used labeled polygons and points to draw attention to certain features. The formatting isn't perfect, it was a bit of a rush job, but just know that if there's something you're wanting to do in QGIS, there are often many different ways to get it to do what you want, including even automating some tasks using Python scripting. This is Site 2, which is a large area of a privately owned property that we explored with landowner permission. We were encouraged to plot points and polygons of areas and objects of interest on an open-source phone app called QField, and then import those into QGIS. This got me thinking of a potential project for identifying historical and pre-contact features at location 2, of which there are many. It would basically be a systematic survey of the entire area using QField, remote sensing, and QGIS to develop a heat map that displays the concentration of anthropogenic activity throughout the region, with layers that organize the data by time period. Given enough time, this could be done. The final open-source remote sensing tool I want to tell you about today is Scaniverse. Scaniverse is an open-source 3D modeling application that can be downloaded to a smartphone to develop 3D models of locations, buildings, and smaller artifacts. Depicted here is a lithic artifact, a flake, that my cohort found at location 2. I collected this imagery data with the Scaniverse app on my phone, and it produced a 3D model of the lithic in situ. I can't help but think of its capabilities for modeling crania, mandibles, and teeth. As someone who's worked with video and photography since 2016 and GIS tools since 2022, I couldn't help but wonder if there was a way to streamline the process of collecting photos for those of us who do not have drones with a pre-programmed flight capability, as manual flight paths for photo collection can be messy and take comparatively more time. So, at Site 1, I took the first steps in testing out an experimental workflow. I captured video transects of that same field location at a 45-degree angle and used a free video editing software to extract image files. One 4-minute flight produced a little over 5,000 images, which is a rather large dataset. I manually selected around 130 photos to generate an orthographic mosaic and 3D model with WebODM, and was somewhat successful. The RGB orthographic itself was low resolution, but the 3D model was almost decent. The next step is to see if I could use coding alongside other open-source tools to select a larger, more accurate batch of photos to be processed by WebODM. This step of the process is still in the works. Once automated selection is figured out, I'll move on to figuring out how to retain the georeference to each individual TIF as they're extracted from the MP4 file. A new and growing field in remote sensing and photogrammetry is machine learning. This is not your grandmother's AI. There are already several use cases for locally hosted AI models being used to identify pottery sherds and human remains. This is the next step in open access digital archaeology. So here are the many reasons why remote sensing and digital data processing are great for archaeology. High-resolution, repeatable, low-altitude documentation, processing accessible via open-source tools, efficient coverage of small, inaccessible, or fragile survey blocks, useful for mapping surface features, and up-and-coming machine learning integrations that will streamline the object identification process. And if you are fond of traditional surveying methods, just know that these two aspects of data collection absolutely complement each other. Regardless of your approach, all archaeological data collection needs a systematic approach, rigorous documentation standards, and someone trained to do the job. UAV data collection in particular, and digital data processing in general, both have some limitations. 1. Weather is a big one. 2. Depending on your budget, you may not always have access to LiDAR, multispectral, or ground-penetrating radar tools. 3. Your GPS and ground control points can play a factor in the georeferencing and model quality. 4. Your computer processing power impacts your outputs. 5. Your project location may have expensive requirements for your drone or its components. These need to be kept in mind when making decisions for how you want to collect your data and how you want to acquire your funding for larger or more expensive projects. So what has already been done for mid to late Pleistocene sites, and what is feasible for the near future? In 2016, Hofmeister and colleagues documented Ardales Cave in Spain using terrestrial laser scanning, real-time kinematic GPS, tachymetric measurements, and three-dimensional GIS integration to portray topographic analysis, ceiling thickness, and lighting simulations. This built upon Hofmeister's earlier terrestrial laser scanning work in 2014. In 2018, Bergquist and colleagues developed an aerial photogrammetric method for recording inaccessible rock art, demonstrating that image-based documentation can extend recording into locations where direct manual access is difficult or unsafe. In the same year, Buzzi and colleagues evaluated an improved photogrammetric approach applied to the Neanderthal skull Sacopastori 1 and compared the resulting model with computed tomography data, suggesting that photogrammetric models can provide accessible three-dimensional records for visualization and shape analysis of fossils. In 2019, Wiseman evaluated recording and interpretation methods for fossil tracks, a form of evidence especially vulnerable to erosion, trampling, weathering, and handling, and found that UAV-based records are useful for site coverage and spatial arrangement, while close-range photogrammetry or other manual approaches may be needed for individual track morphology. In 2020, Reynoso Gordo and colleagues applied remote sensing and virtual reconstruction to Fuente Nueva 3 in Orsay, Spain, a Pleistocene archaeological and paleontological site containing exposed large mammal remains. In 2024, Benraba and colleagues compared manual and remote sensing approaches for gathering data in natural caves and rock shelters. Lastly, in 2025, Muratorianu and Kosak used a GIS-based model to trace potential Neanderthal mobility through the Romanian Carpathians. Their study selected known Middle Paleolithic cave sites and evaluated possible routes through a mountain landscape. The study did not require UAV data to produce usable results, but local UAV documentation could help expand upon the spatial description of important features. So why should we be using these methods more in mid to late Pleistocene research and cataloging? UAS orthophotos have broad potential for future archaeological documentation projects. They can support site monitoring, survey planning, public education, field team coordination, and duplicate recording of the same survey site across seasons. Such data would allow users to compare surface conditions over time, supporting monitoring of erosion, vegetation change, animal disturbance, access routes, and visibility of surface or subsurface features. Locally hosted specialized machine learning models can be used to detect changes or specific objects at sites using remotely sensed data. 3D modeling can also be used alongside augmented reality tools to bring field experience to those with limited travel funds or who attend school online but would otherwise benefit from access to fossils, artifacts, and structures within their area of study. If you made it all the way to the end, put a map emoji in the comments. Special thanks to my Patreon subscribers, Red Fox the Starfish, Nori the Salty Cat, and Gary, Jack, and Mark the Porpoises. The value of your kind support is immeasurable. The next presentation on this topic will cover in-depth previous and future use cases of remote sensing in the study of the mid to late Pleistocene. So stay tuned. And if you want to support the channel, consider subscribing and sharing this video. You can also subscribe for free or paid at my Patreon. Paid subscribers get their names at the end of my videos, along with a few other cool perks. I can't wait to see you back here next week. Same ape channel, same ape place. All locations and tools mentioned here are not sponsored by this video.